Hello friends, welcome back to the third lecture of our week number 3, where we are talking about the application of digital techniques in different measuring instruments or in different measuring methodologies. In the first lecture here, we have discussed about the different number systems and their mutual conversions, particularly the focus on decimal, because that is the one that we keep on using for our day-to-day applications. Whereas in the second lecture, we have discussed about the fundamental components of any digital circuitry, to be more precise the logic gates and their combinations, and we have seen that how by combining different kind of logic gates we can get any kind of combination of digital outputs from a circuitry. And then we have briefly discussed about, or rather in quite detail, we have discussed about two kinds of binary codes, the BCD codes and the gray codes, which are ways of storing some decimal number into their digital format, or I should say the binary format. Today we shall be continuing with the same, and also we shall be learning about how to convert a real life analog input to its digital counterpart. But before that, let us do a bit of exercise like we always keep on doing. Here I have given a simple digital circuitry to you, where there are two inputs A and B, and there are three components. Can you identify these gates from their symbol? Each of these gates have a proper representation, and always you have to identify the nature of the gate from the representation itself. Now this gate number 1, what is this? Yeah, this is an NAND gate. This gate number 3, this is an AND gate, and whenever we have this dot or whatever this extension in front of an AND gate, that represents a NAND, which basically opposes or rather reverses the output of an AND gate. And what about this number 2? This is an OR gate. So one particular combination of output is given. Let us try to form the truth table using the other kind of inputs. So truth table means where let us say A and B are the two, and finally output what we are getting. So our possible combination of input can be 0 0, 1 0, 0 1 and 0 0. One case is already shown here, which is 0 0. Let us try to start with this. So our A is 1, B is 0. Both are supplied to both the NAND gate and the OR gate. So what will be the output of the NAND gate? Here 1 and 0, if we supply them to an AND gate, I am sure you remember that when both the inputs to an AND gate are 1, we get output as 1, otherwise we get a 0. Now it is NAND, which will actually reverse the output. Now here we have 1 and another 0, then the output of NAND will be equal to 1, so we are getting an 1. What about OR? Here 1 and 0 are supplied. If any one of them is 1, then we are going to get an 1. Both the 1s are going to an AND gate, so your output will be 1. So here your output is 1. We can write the first one, which is already shown, that is a 0. What will be the results if we change our output to, let us say, 0 for A and 1 for B? Then again they are going to a NAND gate, so quite similar to the previous situation, the output will be 1, similarly for OR gate it will be 1, and finally we are going to get another 1 here. And what about the final situation where both are zeros, or rather both are 1s? You have 1 for A and 1 for B. If we supply 1 and 1 to an AND gate, we should get 1, but this being a NAND, we are going to get a 0 here, or if I write properly, we are going to get 0. What about the OR gate? It is equal to 1. Actually it does not matter, because whenever one of the inputs to an AND gate becomes 0, final output will be equal to 0. So this is equal to 0, and this becomes our final truth table. Now what we can write in the symbolic math point of view about the nature of the output? So the output for our gate number 1, which is a NAND, that can be written as, if we write A dot B, that corresponds to an AND, and putting this over bar represents this NAND. What about the gate number 2, which is an OR gate? For this OR gate, we can write A plus B, which is how we write OR. So this is for gate number 1, this is for gate number 2, and now they are both are being supplied to an AND gate, so put a dot in between. This is what your output that you are going to get. And also looking at this truth table, you can clearly see that this is actually what we are getting is actually an XOR operation or an XOR gate. That is, by combining these three, we can get operations similar to XOR. So this is a simple exercise that we can have. Let us do one more exercise which is related to the application of the BCD and gray format of storing binary numbers. For that we shall be making use of these tables where we have the decimal equivalent of, or rather binary equivalent for decimal digits from 0 to 15 and also their gray equivalent. Do not need to look at the right hand side of the table, the rightmost column of the table, because gray we can know how to convert a binary digit to corresponding gray equivalent. Let us take a random number. Let us say we have a number 783, then how in decimal, then we can always convert this one to binary, but our objective is not to get the binary version of this, rather we want to get the BCD version of this, binary coded decimal. What is the idea of BCD? There we have to identify the binary equivalent for each of the digits. So, what is the binary equivalent for 7? Binary equivalent for 7 is 01111. Binary equivalent for 8 is 1000, and finally binary equivalent for 3 is 0011. So, that is how it is going to get stored in the computer memory if you want to store in BCD format. This is what you have your BCD version of this. By the way, the white spaces that we are maintaining, like this space here or this space here, in practical computer storage you will not get this. It will be more a continuous representation. Like if your bits are looking like this, these are the bits in your computer memory, then it will be 0 1 1 1. So, this first 4 bit completes the 7, and then immediately the next one will start to store 8, and then the next one will continue for the 3. This way it will get stored in a computer memory. Next is the gray version. We want to get a gray version for this. Now, we have discussed about the gray code and we know that how to get the gray equivalent of decimal digits from 0 to 15. But problem is here our number, as long as we are dealing with a decimal number which is less than or equal to 15, we can immediately get a gray equivalent which is there in the table itself. However, here we are dealing with a 3 digit number. Then how to get the gray equivalent for this? Now, here our number system that we have in the gray, here in each bit we can store decimal number from 0 to 15. Now, if we think about this from hexadecimal point of view, then we can also say that we can store number from 0 to 9 and also A, B, C, D, E and F, that is basically hexadecimal system. So, whenever we are dealing with a decimal number, first think about its hexadecimal equivalent and then convert that hexadecimal equivalent to corresponding gray format. So, here 783 we have. So, let us first convert this to hexadecimal. So, we divide it by 16. So, once we divide it by 16 we are getting 4 and then 8, leaving us 15. 15 actually in hexadecimal sense is F. So, our remainder is F. Then we divide 48 by 16, we are going to get 3 and leaving 0, and then leaving 16 or dividing 16 by 3, nothing there, we are remainder of 3. So, this 783 in base 10 or base 10 we will be having its hexadecimal equivalent as 30F in base 16. So, to get the gray version we have to convert this 30F or each of the digits of this hexadecimal number 30F. We can directly convert that using the table. The other way, let us see how we can do this. First, let us see the binary version of each of these digits. So, what is the binary of 3? Binary of 3 is 0011, binary of 0, that is all zeros, and finally F. F does not have a BCD equivalent, I am just taking its binary equivalent of 15, which is 111. But this is not a BCD representation, because in your BCD it applies only up to this, in this portion. This portion there is no BCD equivalent, BCD is only up to 0 to 9. Here we are just trying to convert the binary equivalent of each of them to the gray. So, how to get the gray equivalent for this? First, remember the rules. The most significant bit will remain as it is, which is 0, so that remains 0. To identify the second digit in the or the occupant of the second bit in grayscale, we have to take the XOR of the first two, here both are 0. So, its XOR also will be equal to 0, then 0 1 XOR will be equal to 1, finally 1 1 XOR will be equal to 0. So, next all zeros, so its gray equivalent also will be equal to 0. All ones, first one is 1, then if we combine these two, 1 1 XOR equivalent is 0, then we combine these two, it is 0, finally combine these two, XOR equivalent is 0, and this gives us the gray representation of our original decimal number 783. Again the white spaces should be neglected, they will have a continuous representation somewhat like this. So, this one is the BCD representation of 783, this is the gray representation of 783. Depending upon in which format you are storing the number, the same will go to the register of your computer or in the memory of this. So, we have seen now, or we know now how to convert a decimal number to its gray or BCD equivalent and store that in memory. But numbers are not all, rather there are several situations we have to deal with other characters also, and that takes us to the next one, which is the alphanumeric code. Another type of binary code, sometimes in even other number format also we can be stored, but these are alphanumeric code which all of you are very much aware about, or we always keep on using this, because just think about a computer or think about your mobile phone. It is not that always we are typing numbers, you are always typing texts. So, whenever sending a message to someone, whenever typing an email, whenever typing a WhatsApp message, what do? We keep on typing the characters, A, B, C, D, these characters, different symbols, plus, minus, etc. The even more advanced versions of that, different emojis or smileys that we keep on sending. Now, those are not numbers. Then we definitely have to convert them to corresponding binary format, and then only we can transmit that via the digital networks. So, that is what comes under this alphanumeric code category. There are several alphanumeric codes which have been proposed throughout the historical development of such digital networking. The most from the historical point of view, the first one I should say is the International Morse Code proposed by Samuel Morse in 1837. Now, have you heard about this? This is how a Morse code looks like. All the characters, firstly it has only the uppercase letters A to Z and the digits 1 to 0, and in the international version of this one, several of the symbols are also included like shown here. If you see properly, each of these characters can be represented by a combination of dots and dashes, like here the colors are given just to distinguish between them, but practically they all may be in black. So, there are dots and dashes, and the combination of these dots and dashes represent different kinds of characters, like A is given as 1 dot followed by a dash, and the number of characters to represent any corresponding character, number of characters in Morse code required to represent any normal character, they are not same. Like look at this E, here there is only 1 dot to represent E, whereas if you take any another one, say number 1, here we have a dot and then 4 dashes. So, they does not follow any particular pattern, this is just something that concerned persons have to remember. But have you seen or have you heard about any application of the Morse code? This is what that used to get used in the telegraph system. Now, in India the telegraph system has been abandoned, it has been withdrawn by the postal department, but it is still there in different other places of the world and also used in different other coding or communication systems, and that is what is used or what they use is this Morse code or the International Morse code. So, the biggest problem of this one is the non-uniformity or lack of any particular structure, like the number of bits required to represent different characters may be different. That lead to the next one, Wideout Code proposed by Wideout in 1870. Here each character is represented by a 5-digit formation. Thus, just look at this particular portion. Here each characters are given 5 bits to be occupied with, and some of them will be occupied by black dots, some of them will be by white dots, and accordingly we keep on going. Again, there is no particular pattern between successive numbers, like look at A and B. A is having a single dot and followed by 4 white spaces, whereas for B 2 white space, then 2 dots and then another white space. So, no particular pattern. you somehow have to remember this, but its advantage over the Morse code is that each character occupies equal number of bits, which is 5. Then it kept on evolving these different alphanumeric codes. Different countries kept on using different kinds of formats. In fact, they still keep on using different kinds of formats, but there was a need of standardizing this, and so it came the ASCII, American Standard Code for Information Exchange, which is something which was used from the very early days of computers. It is a 7-bit code, thereby allowing a total of 2 to the power 7, that is 120 total characters can be represented. Here each character can be represented by a 7-bit formation, so a total of 127 characters can be considered under this ASCII format. Out of this 128 characters, 95 of them are printable. 95 printable, how we can get? We can have 26 uppercase letters, that is A to cap Z, then 26 lowercase letters, small a to small z, then we have 10 digits 1 to 10, and there are 33 symbols, just one representation like this. These are the printable characters, you can see them and their corresponding binary equivalent. Each of these printable characters have got a binary equivalent, and that follows a particular structure. Like just try to see at what is 0. First 0, this is your 0 corresponding binary equivalent you see, and then when you move to 1, there is only change in one binary digit, which is the least significant bit that changes. Then the 2 is the next one, means once you add 1 with the binary representation of 1, you get 2. And the same way look at the uppercase letters. What we have as A, if you add 1 to the corresponding binary representation, you get B. So, that way it allows some kind of mathematical operation. That means sometimes we also write in this way, like if we write A plus say 10, then we should get which character? A is this, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we are at K. So, these are this way we can represent, but here actually A and K represents, and also 10 represents their binary equivalent, and this is somehow sometimes we write in ASCII sense. Another interesting thing that you can observe, the difference between lowercase and uppercase letters. Whatever the position of the lowercase letters, each of the lowercase letters are equally positioned or at an equal distance compared to its uppercase counterpart. Actually, they are 32 characters apart. So, if we write A plus 32, means I am talking about the binary equivalent of A, and if we add the binary equivalent of 32, you should get small a. So, this way we can easily shift easily can shift or swap from one letter to jump from one letter to other, or rather one character to another one, and we can sometimes perform quite a bit of mathematical operations on them. So, this is what we have in ASCII character, but here 95 of them are printable. There are 33 non-printable characters as well, like none shown in this particular table. Here generally your machines are 8-bit machines, or rather they can be much higher bits also, but in 8-bit machines it is occupying 7-bit, and so 0 is generally is the one that is used as the most significant bit, like shown in this table. For all of them, the most significant bit is occupied by 0. This is a more comprehensive list, sometimes called the 1968 version of the ASCII code. Here if you check from starting from the first one up to this particular one, this entire first column, they are all non-printable characters, and you have another one here, the del. These are all non-printable characters. All these non-printable characters were used in the early days of the computers or development in digital instruments, for performing different kind of control operations like the printers, etc. Most of them are obsolete, apart from just a few handful of them, all others are obsolete and non-relevant. These are the details of all these non-printable characters. Only a few of them, like the line feed, carriage return, the delete, these are the ones that are still under use. Now, how to use this ASCII character set? So, let us take an example. Say we want to write help. So, using your using the keypad of your computer or mobile, you can always type this HELP, but it is not stored in the memory of the device, or it does not get transmitted as this HELP, rather it gets transmitted in their corresponding ASCII binary format. So, what will be the ASCII representation for each of them, or ASCII counterpart? So, H, where is H in this? This is H. So, in the memory it will be stored as 0 1 1 0 1 triple naught, then comes E. So, this is your E, just 3 stages back from there. So, it continues like this with this A, E rather 0, I am writing in the next line, but actually it will continue just 0 1 0 1, then we have L, this is your L. So, it is 0 1 1 0 1 1 0 0, and finally P, just find P from there. So, this is P 0 1 1 1 0 0 0 0. It will be a continuous chain. Just because of the lack of space, I have written it comprising of 3 lines, but it is a series of digits, zeros and ones like this, 8 digits or 8 bits corresponding to each of your characters. So, total 8 into 4, 32 bits, 32 numbers of zeros and ones combining together represents your original word help, and this way we can form the ASCII counterpart for any of the printable characters appearing in this table. But one issue is that all the digits that are appearing, or all the characters that are considered in this ASCII set, they are just common characters to English, the upper and lower case English letters and or English alphabets and the digits. But there are several other languages and infinite number of languages and also characters that appears in the world, and therefore, ASCII character set is not sufficient to represent even several of the English language, even several of the European languages like French or German. They have several other characters also which are very frequently used, and if you want to include the Asian languages like Mandarin or Japanese, they have huge character set to be considered, or even the Indian languages. There are so many languages in India, each of them having a different script, or many of them having a different script. The script of the North Indian languages does not match with the script of the South Indian languages. So, each can provide certain new characters. In that case, ASCII fails very much. So, there are lots of efforts to improve that, to consider a more number of characters in the same data set within the scope of the same data set by expanding the number of bits involved in this, and expanded ASCII, which is an 8-bit character set that was proposed by certain companies. It is an 8-bit, so it considers 2 to the power 8, that is a total of 256 characters, but that even that is also not sufficient. Another character set that is quite commonly used, that is EBCDIC, or called Extended Binary Coded Decimal Interchange Code. It is an 8-bit code, so it can represent 8 characters using its binary format, and it is developed by IBM, and generally it is found application in IBM, specifically in IBM machines and by certain other companies, but strictly speaking its application is more restricted to IBM machines only. This is a kind of representation. I would not suggest you to try to go through this, because it is not a very of course IBM, it is standard for IBM, but it does not follow any regular pattern like ASCII. There is no direct correspondence between the upper and lower case letters, and also all the character that appears in the ASCII, even they don't appear in this character set, and therefore it has only limited application. And despite having double number of characters than ASCII, it still suffers because it can't represent all those other characters that are possible. So, effort was on to expand this alphanumeric code center by using higher bit systems. This ASCII and EBCDIC encoding and their variants suffer from the similar limitations like insufficient number of characters, which I have just mentioned, and their incompatibility between each other. All characters in ASCII does not appear in EBCDIC and vice versa. So, we have this Unicode nowadays. The International Organization for Standardization, or ISO, and Unicode Consortium, they together has developed the Unicode. It is a 16-bit code system. That means it can represents 65,536 number of characters total, which generally involves almost all major languages that all the characters that appears in major scripts throughout the world. And at the moment you will find this Unicode in most of the modern operating systems, Android or Microsoft or Linux based systems. They all generally use Unicode nowadays. But that is even not sufficient also for certain languages. For certain characters appearing certain scripts still are absent in this Unicode, and there is always scope for further improvement. So, presently Unicode provides multilingual support, and also it incorporates several mathematical and technical symbols. Thereby, for all the technical writings we can easily use this Unicode, at least for the moment now. But the 16-bit itself may not be sufficient in future, and in next 5 years time you may find a modified version of the Unicode appearing. There is another kind of code I would like to mention very briefly, that is the barcode. I am mentioning this because I know all of you are very much aware about this. Barcode is a combination of several black and white lines simultaneously or side by side. So, in all barcode you have a particular kind of pattern. There is a couple of buffer zone or quiet zone on either side, and then you have a start character. This portion is a start character which will indicate to the scanning device that exactly in which position, from which position it should start scanning. Similarly, the stop character here which indicates the scanner exactly where to stop the scanning, and then you have the data message in between portion, and we have a check digit which generally checks whether the reading is correct or not. Barcodes, you will find there are 4 kinds of characters. There is a narrow bar and wide bar, and similarly narrow space and white space, or you can think this way, there are black lines, there can be thin or they can be thick. Similarly, white lines can be thin or thick. Generally the ratio of their thickness varies in the range of 1:2 to 1:3. Quite often you will find the ratio as 1:2.5 to be an optimum one. I will not go into the detail of how barcode came in or exactly what are the formats, and because there are several kinds of standards for barcode, this is just one of the formats. Generally in each barcode you will find there are 7 parallel lines to represent each character. This is one representation, just look at one. There are 2 white lines, then 2 black lines, then 2 white lines again, and finally 1 black line, that is 1. Look at 6, there is 1 white line, 1 black line, then another white line, and then 4 black lines together. This portion there are basically 4 black lines together. Or look at 0, what you can find? There are 3 white lines in this zone, then 2 black lines, then 1 white, and then another black. So, this way the different characters can be represented in the barcode. These are just digits in one of the standard systems. Similarly, any kind of alphabet can also be represented here, and that is something that you are very much aware about. You can see the application of this one whenever you go to some kind of shopping where they keep on using this. So, this is about different kinds of binary codes that we keep on using. We have learned about BCD and gray codes, which are used for storing numbers or digits in the binary format, and we have discussed now about the alphanumeric and also the barcodes. But now we have to check exactly how we can convert a real life decimal signal, or I should say an analog signal, to corresponding binary format. So, let us move to the analog to digital conversion. In any analog to digital converting instrument, you will find there are generally 2 steps. The analog signal that you have, or I should say there are 3 steps. First, there is a sampling step, that is a analog signal. From there certain specific number of data points are collected, which is called the sampling. Thereby the continuous signal, this continuous analog signal gets converted to discrete signal, where a particular number of generally a specified number of data points are available over a period of time. And then using that quantized data, the sample data, we get a quantized signal which is performed by this quantizer. The digital instrument generally performs this quantization operation, and then we have the encoding. So, in the quantization step, the analog signal is broken down into series of finite states, and then during encoding a number or a digital word, generally a number, is assigned to each of those states to get the final corresponding digital output. Like the example shown here, you have the analog signal at the top, and during the sampling step we have collected a particular number of data points. Depending upon the resolution of your instrument, depending on the sampling speed of the instrument, we can collect a particular number of sample, which are then quantized and encoded to the concerned format that we want. Here one important thing, without going into the detail of the electronics, the frequency of collection of the signal or the sampling speed itself is very important to ensure the correctness of the data. To prevent aliasing, which is actually the frequency of outside the desired band appearing within the bandwidth of interest, we need to ensure that the signal frequency is less than half of the sampling frequency. Preferably we want the sampling frequency to be much higher than the signal frequency. Sampling frequency is given as like over a particular time interval how many samples you have collected. So, like in this example there are 3. So, if this time interval is 1 second, then your sampling frequency is 3. This higher the sampling frequency, it is always better, your instrument will always be able to give much better representation of the actual analog input. So, we always want the sampling frequency to be high, and to the lowest limit it should be at least twice of the actual signal frequency. So, this particular rule is called the Nyquist rule. So, now in any digital instruments we have the analog input coming in, and quite often we generally have a reference input also. This reference input is compared with the analog input to provide some kind of modulated signal which is sampled then quantized depending on the number of bits that the instrument is using, and then we get the digital output at the end. General input voltage, let us take an example that our instrument is able to operate within the input voltage range of 0 to 10 volt, and we are having a 3-bit AD converter. AD converter is this particular way we represent analog to digital converter. Similarly, DA converter, D/A represents digital to analog converter. Another way of writing this is, we shall be using this format very soon, ADC, that is analog to digital converter. Similarly, this is also written as DAC, digital to analog converter. So, we are using an 3-bit AD converter. So, 3-bit means how many levels it can allow. 3-bit means how many correspondingly how many decimal values that we can allow. So, we can have 2 to the power 3, that is 8, that means 8 levels can be allowed within this range of 0 to 10 volt. So, if we divide this 10 volt by 8, what we get? We get 1.125 volt. So, that gives you the resolution of the instrument, and this is what we have. So, we can divide this entire voltage range of 0 to 10 volt into 8 distinct levels, each of them having a span of this 1.125 volt. So, anything appearing between 0 to 1.25 will be identified as 0 or the state number 0, then 1.25 to 2.5 will be identified as 1. This way finally, anything appearing between 8.75 and 10 volt will be identified as a level number 7 or state number 7, and then convert all these 0 to 7 into their digital equivalent. So, we know how to convert. The first one will become in 3-bit representation, it will become 000, and the final one, that is 7 in digital or state number 7, will become 111. This is how we get the digital equivalence of the original input signal. So, the input signal that you have provided in 0 to 10 volt, as our instrument is 3-bit, so we are converting that to 8 different levels, and we are getting the equivalents. For anything appearing between, say, in this range of 3.75 to 5, we are getting this, the digital equivalent as 011. Let us say your input signal is 6.391. So, exactly in which level it appears? 6.391 appears in this range of 5. So, its digital equivalence will be 101. So, another way, if you think about, if your digital input is 7.001, that will also appear in the same range. That is, any value your analog value appearing within this range of 6.25 to 7.5, your digital instrument will not be able to classify between them. They will represent all of them by the state 5 or 101 as the output. So, that is one way of drawback of your system. To rectify that, we need to go for higher bit system. Like think about, if your instrument is a 4-bit one, then what is the small width of each of those states, or how many states it can measure. So it will be able to measure 2 to the power 4, that is 16 number of states, that is starting from 0 to 15 states it will be able to measure. And what will be the width of each of these states, that will be 10 volt divided by this 16. So I think it is 0.625 volt. So within a span of any signal appearing within a span of 0.625 volt will be identified as 1, and then accordingly it will be dividing the entire span of 0 to 10 volt within 16 levels. So this is what we call as resolution, or sometimes also called analog quantization size. It gives a measure of the number of digital level the converter can produce. So it is just I have mentioned V max minus V min by 2 to the power n is the resolution of your instrument. And finally we get a representation like this. Like for the 8-bit one that we are talking about, anything appearing within this particular zone, any signal appearing within this particular zone, they will be represented by this particular digit. Similarly, anything appearing within this particular zone, they will all getting a correspondence to this. So we have to be careful, like if we want very precise measurement, a difference between say this particular let me clarify this mess here, say this is one analog value and this is another analog value, and we want to make a distinction between them. Your digital instruments may not be able to do this because they are falling within the same state level. So this is again just repeating the same, the resolution, any value appearing within this signal range will be given the same digital level, and that will continue for each of the digital levels, and the only option is to increase the resolution of the instrument, and that is to allow more number of states within the range of voltage that you are dealing with. This is called the quantization error. If you remember, in our first lecture in this particular module, we mentioned about the quantization error, that is analog signal is independent of quantization error because you are not doing any sampling there, whereas in digital signal we are doing the sampling, leading to this quantization error. Another point that comes into picture is the sampling speed. How many samples you are collecting over a particular interval. Like in there are two situations shown there. In the first case we are collecting less number of points, in the second case we are collecting double number of samples, and definitely your resolution is much better because you are able to measure, like here over anything appearing with this span is given the same value, whereas it is a much smaller span in the second case. There are two examples shown. First one is having low resolution, or rather quite big resolution and low sampling rate. Second one is having more precise resolution and higher sampling speed. So, and definitely the second one will give you much better digital representation, because you can see in the first one this entire portion, while the curve is changing like this digital signal is stuck at the same point, whereas here it is again broken into 3 or 4 different levels. So we can have much better representation when both resolution and sampling speed are better or favorable. Now there are different types of analog to digital converters. We shall be discussing about some of them. Each of them has its own shortcoming, each of them has its own merit. Some of them are very fast, some of them are more precise than the others, some of them can be very accurate but are very costly or complicated in their operation. So let us just quickly check the way some of them are operating. First one is the digital Ramp Adc. In this is the circuit diagram for this. At the moment there is no need to go for the circuit diagram. The digital Ramp Adc is a very simple one, but it has several limitations. It is probably the first in this line. Here we have a free running binary counter. So we have this is the counter, like the diagram that is shown here is of an 8-bit thing. So you have a free running binary counter. Free running means, like initially the counter is set as all zeros, then it changes the first digit to 1, and then after a particular time interval it again changes to 1 0, then again the same time interval apart it changes to 1 1, and this way it keeps on changing 0 0, this way it will keep on changing without any control. So this is what we refer by a free running binary counter, and the output from this free running binary counter is supplied to a digital to analog converter. How it is done, that we shall be learning in the next lecture, that is the digital to analog conversion. But the output of this free running binary counter is supplied to a digital a DAC or digital to analog converter, and the output of this DAC, this particular one, is directed to a comparator where it is compared with the actual analog input. So, as long as your analog input is higher, then the counter will be allowed to run. But whenever the output of your digital to analog conversion that becomes higher, then of course at that instant you have crossed the analog value. So, we should stop. Just look at here, your analog value is this over this range, and your counter is increasing, the voltage corresponding to digital to analog conversion, that keeps on increasing. Just at this particular point it is touching the analog signal or maybe just crossing it. So, this counter, this comparator will activate a control mechanism which will stop the counter, thereby giving this particular digital output value, and the counter will be set back to 0. So, the objective, or rather the operation of this counter, this comparator rather, is to ask the binary counter to stop as soon as the output of this DAC becomes greater than the actual analog input, thereby you get this. Immediately the counter comes back to 0, it comes back to 0 and then again continues to operate, that is 1 bit at a time, it keeps on increasing, and it continues to increase till again it encounters analog signal like here. During that entire period your output is stuck here, then here you are getting another output for this. So, this is a very simple mechanism of operation, but what do you feel, what are the shortcomings it can have? Definitely it is quite slow, because every time for you are starting from 0, you are continuing till you meet the analog signal, and as soon as you meet the analog signal you fall back to 0. So, it is very slow in its operation. The sampling time keeps on varying with the input voltage, like you can see in this case the one sample is collected here, the next one will be collected here. So, this is the span that depends upon the input voltage value which is high. Like in this case, one sample is collected here, the next one is collected here, it is a much smaller span because the input voltage is like that in this particular time. So, the sampling speed or sampling time keeps on varying with the input voltage itself, which also may not be a very favorable one. Like we can see here, this is the gap during 2 successive samples, whereas here the gap is much smaller. In several applications this can be quite disastrous. So, we do not want this to happen in many practical applications. So, one big problem for this digital ramp ADC is it is slow, and second is this varying sampling time. It is really slow, one of the slowest among all the ADCs that we are discussing, but advantage is it is very simple, it is cheap and easily operatable. Next we move to the single slope integrating ADC. In the single slope integrating ADC we have a capacitor, this is the one. This capacitor is charged by a constant current till the capacitor voltage reaches the analog input. That is the output of this capacitor is supplied to this comparator, where it is compared with the actual analog input which is there, and as long as the analog input is smaller, the capacitor is allowed to be charged till they reach the output voltage. When the comparator output becomes high, the capacitor discharges back to 0. That results in a sawtooth waveform just like this. Over this, the capacitor output is increasing, capacitor is continuously becoming charged, so voltage of the capacitor also increasing. Just here it meets the analog signal, so that provides you first digital output and capacitor immediately discharges to 0. And again it continues till it meets another analog signal again, thereby providing the second one. So, we get a sawtooth kind of waveform as the output of this capacitor voltage. In the previous case, if you remember, you had a staircase kind of configuration, a staircase kind of output going to the comparator, whereas here we have a ramp or we have a continuously increasing one. So, the time taken by the sawtooth waveform to exceed input is measured with a digital clock, and the time required depends again on the input voltage, and also it depends on the combination of the corresponding circuitry, that the value of the capacitance, corresponding resistance, the reference voltage also which is there with the capacitor itself, it depends on all of them. So, it does not involve any kind of digital to analog conversion, so the circuitry is much simpler it is cheaper also in that sense, but it suffers from all the disadvantages that a digital ramp one have, like low resolution, slow and also varying sampling speed. You can clearly see here, this is the sampling interval, where the sampling interval is much slower in this case. So, it has varying sampling time, and there another problem can be the calibration drift with aging, as the rate of integration and rate of counter independent of each other. That is, as it is continuously used, the capacitance values etc. may change, thereby severely affecting the output of this. One improvement on the single slope integration ADC or single slope integrating ADC is the double slope one, where instead of being charged by a constant current, the capacitor is charged by a current proportional to the input voltage, thereby reducing the operation time quite a bit. Rest of the operating principle remains the same. If someone is interested, you can search over the internet for double slope integrating ADC. But we shall be talking about now the successive approximation ADC, which is the probably the most widely used and popular one. It has a conversion time constant, maintained constant and proportional to the number of bits in the output. Like in the previous two examples or previous two converters, we have seen that the conversion time depends on the input signal itself. Depending on the that is, in both cases, whether you are going for a staircase approach in the digital ramp or whether you are going for a constant current approach in case of a linearly increasing voltage in case of the integrating ADC, we have a varying sampling time, whereas the biggest advantage for successive approximation, here your conversion time is constant and is proportional to the number of bits in the output, which should be the ideal one. Now, unknown analog input voltage is approximated using an n-bit digital device. One bit is changed at a time, starting from the most significant one and finishing with the least significant one, and there is a register which monitors the comparator's output to see if the binary count is greater than or less than the analog voltage, and accordingly it adjusts the bits. It stops when the output of your DAC becomes equal to ADC. So, the final conversion time is equal to the number of comparison times the clock period, and number of comparison is equal to the number of bits. Now, seems quite obscure. Okay, let us check with an example. We have a 4-bit ADC which is receiving some analog input of 6 point something volt, and it has a reference of 10 volt. So, what will be its resolution? It is a 4-bit. That means, it can allow a total of 2 to the power 4, that is 16 levels, and there are 4 bits. So, each of the bits, the first one will correspond to 2 to the power 0, next one 2 to the power 1, this is 2 square, and finally 2 cube. Total 16 level it can provide, and what is the resolution? That should be equal to 10 volt divided by 16, so 0.625 volt. So, resolution is 0.625 volt. So, what is the voltage corresponding to each of them? First one is 0.625 into 2 to the power 0, that is 0.625 volt itself. Second one 0.625 into 2 to the power 1, that is 1.25. Third one 0.625 into 2 square, that is 2.5, and the most significant bit corresponds to 0.625 volt into 2 cube, that is 5 volt. So, each of these have some input. What I mean here, like suppose you are having a 1 here and all zeros, then corresponding digital to analog conversion will return a 5 volt, whereas if you are having suppose 1010, then corresponding digital to analog conversion will return a 5 volt plus 1.25, that is 6.25 volt, and precisely that factor is used in successive approximation ADC. This is an example. Here the output that, or rather the analog input that we are trying to convert is this. So, we start from the most significant bit, we set all these bits to be equal to 1, or rather the register of the instrument sets all of them to be equal to 1, and we start with MSB. When it is at MSB, or I should say initially MSB is set to 1, others are set to 0 by the register. So, when it is 1, we are getting 5 volt, and the comparator checks whether the input is greater than or 5 volt, or not. In this case it is greater, so this 1 is retained. Now, it moves to the second one, which was initially 0, now it is set to 1. So, how much is your output? 5 plus 2.5, that is 7.5. 7.5 volt is the output of your DAC, and whether it is greater or not, it is lesser. so it goes back to 0. Now the third bit that goes to 1. So how much is your output from the DAC? Remember, MSB has already been set to 1, second one has been set to 0. So you have a 5 plus 5 plus 1.25 volt, so 6.25 volt. Whether it is greater, comparator checks and the analog input is greater than that. So this 1 is retained here. So 3 bits are final, 1 0 1. Finally, the least significant bit is set to 1 and comparator checks whether the input voltage is greater than 6.875. No, it is less than that. So you set to 0 and a final output becomes 1 0 1 0. This is the digital output that you are going to get from this. If we can increase the number of bits, then we can get even more number of binary digits to represent the same signal. This is kind of circuit diagram where this is a successive approximation register which keeps on changing one bit at a time, most significant bit first, like when it is 1, others are set to 0, it checks the output of this DAC to this in this comparator, and depending on the result of that, it keeps this one either as 1 or goes back to 0. Once this is set, then it moves to the next one which is set to 1, and this process is repeated till we finalize what is the digit in the LSB. You can think the DAC output keeps on changing like this. Your analog input is known, which is a constant, and the DAC output, when you set the most significant bit, you have set up a big one, then there is a smaller, much smaller change. Finally, we are going back to the analog input. If we think an algorithm point of view, just what I mentioned, first all bits are cleared and we start with most significant bit. MSB, like here, first MSB is set to 1, others are all 0. So if the DAC output is greater than this, then if DAC output is lesser, then it will remain as 1, otherwise it will go back to 0, and then it moves to the next significant bit. This way we keep on moving till the least significant bit. Depending on how many number of bits you have, we know the number of times we have to compare, and accordingly the total time required for conversion is fixed. It has medium accuracy level, depends on its own resolution, but the constant conversion time is the biggest advantage. It is a high speed, reliable and high resolution device, can go up to 16 bit, which is probably the highest among all the ADCs. Then it consumes low power and cost. It is a good trade off with the speed. The speed is low, or rather I have mentioned that the conversion time is constant. I have mentioned high speed, but compared to if your other ADC, speed is low. It is slower as the resolution keeps on increasing. It is slower because like 8-bit cases we have to compare 8 times, whereas in 16-bit cases we have to compare 16 times. So the conversion time keeps on increasing, and the circuitry is a bit complicated because of all these comparators involved, or I should say all these comparisons involved. You have to modify each of the bit once at a time. So the next one comes is the flash or parallel ADC, which is probably the simplest one to understand from operation point of view, and it is very fast. It gives direct measurement with 2 to the power n minus 1 number of comparators. How that is done? Look at the circuitry. Here we are dealing with a 3-bit output system. So your total number of levels it can measure is 8, which is 2 cube, that is 8. So we shall be having there are 8 minus 1, that is 7 number of comparators will be there, like shown here. Now there will be a reference voltage, this is the reference voltage, and then there are 7 number of resistors, equal value of this resistor. You can see all this R, there are 7 number of resistors and 7 number of comparators. This chain of resistors are connected to the ground. So what is the current that is flowing through this? Can you calculate? The Vref is the voltage that you are applying on one end, other end is grounded, there are 7 number of R resistance. So the current that is flowing through this I is equal to this Vref divided by 7R, that is the current that is flowing through this. Now each of the comparator in one side that is connected to the input voltage, on the other end it is connected to either the Vref or a modified version of that. Like the first one, the top one is connected with Vref, second one is connected when the Vref connected to the Vref through one resistor. So what is the voltage at this particular point? It is Vref minus I into R, I into R is the corresponding loss, that is Vref minus Vref by 7 R into R, that is 6 by 7 Vref. So, the second one is subjected to 6 by 7 Vref. Similarly, the third one will be subjected to I should say this particular line, this particular portion it will be subjected to 5 by 7 Vref, and this way it will keep on increasing or decreasing, rather this will be subjected to 4 by 7 Vref, 3 by 7 Vref for this, 2 by 7 for this, and this one just 1/7 of the Vref that you are providing. So, the reference voltage for each of the comparator that keeps on changing, and that is compared with the input voltage. Now, depending on the value of your input voltage, one or more number of comparators will give you positive output and some of them give you negative output. Like suppose if your V in is in between 3/7 Vref and, or I should say it is greater than 3/7 of Vref, but it is less than of 4/7 Vref, then it is greater than 3/7 Vref, but more than 4/7 of Vref, then the what output you will going to get from that? The first one will give a positive output because here V in is greater. Second one where you are in the first one you are supplying V in and Vref, so it will give you a negative output. Second one, the reference is 6 by 7 of Vref, so it is negative. It is 5 by 7, so it is negative. This is 4 by 7, this is also negative, but here the reference is 3 by 7. So, this will give you a positive one, this is positive one, this is also positive one. So, for this particular input voltage, it is giving you positive output from 3 of the 7 comparators, whereas others are negative. So, the entire array is clocked simultaneously and decides in parallel, and if the comparator with the reference is less than the input, then we get 1, otherwise 0. And now only the one that is having the highest order, that input is considered. Like here 3 are giving positive, so only this one will be considered because here the reference is the highest, and then accordingly your encoder decides which should be the binary output. This is the way the final signal looks like. It is simplest in terms of operation, very fast. That is why we call it parallel, because all encoders, or rather all the 7 comparators are working parallelly. It depends only on the delay that is associated with the comparators, otherwise it is very fast. It is able to produce nonlinear output as well. That is one very important application. Like here all these 7 resistors are equal in magnitude, but if sometimes we want a non-equal reference or we want to have a non-linear conversion, then we can change the value of these resistors itself. Therefore, we can get non-linear output as well, which none of the other variation of these ADC converters or ADCs can give. But its resolution is quite low, expensive and most component intensive, because like in this case for a 3-bit output we are needing 7 number of comparators, whereas think about if you are talking about an 8-bit conversion, then you will be needing 2 to the power 8 minus 1 number of comparators. So, number of comparators keeps on increasing rapidly with the number of bits, output bits. Accordingly, it becomes expensive and very difficult to design, and the power consumption also will keep on increasing. Yes. The final one I shall be mentioning very briefly. It is called the sigma delta ADC, or sometimes the opposite, the delta sigma ADC. Delta in Greek letter represents the difference, sigma represents summation. That is what this one does. It has one integrator which does the summation, one comparator which takes the difference, and then 1 bit DAC. The DAC signal is subtracted from the analog signal and fed to the integrator. Here this is the integrator, this is your difference, and depending on the output of this, it is supplied to this DAC which converts 1 bit at a time, and then we get a stream of zeros and ones, from where through the filtering process we get the final output. I am not going to the detailed procedure of this because this is a bit complicated and not required also from the purview of this course. But its advantage is it gives the highest possible resolution and also very high accuracy. it permits noise shaping and also much less number of components, particularly when you compare with the successive approximation one. But it is again a bit slow because we get just one bit at a time. It has a limited input bandwidth. Sigma delta ADC probably is the most accurate one among all that we have discussed, but the successive approximation one is the one that is most commonly used in general purposes. So, that takes us to the end of the day, where we have discussed about the alphanumeric and barcodes, and we have discussed the principles of AD conversion, the role of the resolution and sampling rate, and finally, we have discussed about different types of ADCs. We have discussed primarily about 5 different types of ADCs: the digital ramp, then the integrating ADCs, successive approximation ADCs, flash ADCs, and also the sigma delta ADCs. Flash or parallel ADCs and successive approximation, these two are the most popular one, whereas sigma delta is the most accurate one. So, that is it for the day. In the next lecture, which I hope to be a smaller one, where we shall be discussing about the other process, that is the digital to analog conversion, to finish up this particular week's work. So, thanks for your attention. We shall be meeting very quickly.